This presentation is about the theory of constraints, which is the management philosophy that's taught in the book The Goal. When the chapter opens up, things aren't going very well at the plant. Overall, the plant's not doing as well as management would like it to do, and in particular when the book opens up, Bill Peach has come into the plant and he's got a hot order that he wants to expedite. And in order to do that, in order to run the hot order, in other words, an operator in one of the work centers is going to have to stop doing what he's doing and run a piece for the hot order. And he doesn't want to do that. And the reason he doesn't want to do that is because he doesn't want to break a setup. In other words, he's already set up for one job, he's running one job, and to work on this other material, he's going to have to stop what he's doing, set his machine up all over again, run that material, and then reset up again to finish the job he was working on in the first place. And he's not very happy about that. And that's not unusual. One reason that we try to avoid doing that often in operations management is because of efficiency considerations. And to think about efficiency a little bit more formally, efficiency is what we produce divided by some standard rate of production or amount of production that's expected during a particular time period. So it's a ratio of what we actually do to what's expected of us. We'll talk a little bit more about efficiency a little bit later here in the talk, but just to give you kind of a feel for what that's all about, because efficiency is really kind of a big deal as we open up in the goal. In chapter 2, actually in chapter 1, Alex tells Peach that Alex needs more people to do what he needs to do in the plant, and Peach's rationale for telling Alex that he cannot have more people is that Alex's efficiencies are weak. In other words, he's not getting the job done according to the performance measures that are being used at the time. Overall, Alex is very frustrated. In chapter 2, he says that the plant should be making money. Nobody's cut costs the way he has. Overall, his efficiencies are good. They've got robots, they've got a new computer system, and so on. And then in chapter 3, Peach kind of drops a bomb. At this point, Alex is in a meeting at headquarters, and in this meeting, Peach says that the division is going to be sold if there's not a turnaround by the end of the year. During this meeting, Peach says that the future of the business depends on the ability of the business to increase productivity. Note that he really doesn't define what he means by productivity, and later on in this chapter and the next chapters we get into quite a bit of discussion about exactly what productivity actually means. But during this meeting, Alex does what a lot of people do during meetings, and maybe even during college classes. He starts to daydream a little bit, and he starts to think about his meeting with Jonah in the airport. And when he and Jonah meet in the airport, one of the things he tells Jonah about is the robots that they recently installed in the plant. And the robots had a pretty big impact on productivity. According to Alex, the robots increased productivity by 36%. And when Jonah hears this, he's pretty excited. He says, "You mean you increased the productivity of your plant by 36%? And of course, Alex thinks what a lot of people think about their college professors. Recall that Jonah is a former college professor of Alex. He thinks, well, this guy doesn't really know very much about the way business really works, right? He doesn't really understand the real world very well. Because what does Alex really mean when he says that the robots increase productivity by 36%? Well, he means that there was a 36% increase in one department. When they look at productivity conventionally, like a lot of organizations, they look at productivity on a resource-by-resource basis, on a department-by-department basis, thinking that productivity of each department is going to add up to the productivity of the whole. And when they say, what improved, he means that efficiencies increased, cost per part decreased. Those are the two major performance measurements that they're looking at. So perhaps efficiencies increased 36% or cost per part decreased 36%. Jonah asks him some pretty interesting questions. Jonah actually makes a couple of predictions after he asks the questions, and he predicts that inventories have gone up, gone through the roof actually, and that late orders have gone up quite a bit. And that kind of puzzles Alex because as it turns out Jonah's exactly right. Alex just can't really figure out why at this point. And in a couple minutes we'll talk a little bit more about how Jonah is able to correctly make these predictions. But it's kind of interesting coming back to the concept of productivity that towards the end of the chapter Jonah tells Alex that productivity is meaningless unless you know what your goal is. So Alex heads back to the plant, and he doesn't go back to the plant right away. He does a little bit of thinking before he gets to the plant, and he decides that the goal of the business should be to make money now and to make money in the future. When he heads into the plant, he sees something that he's not very happy about. He sees three people in the plant just kind of sitting around, and he gets kind of upset, and he tells the supervisor to make sure these guys get busy. And the guys get busy. They start pushing around a broom and moving some material around. But the question is, are they really being productive? Just because they're doing stuff, are they really helping the company move towards its goal? This kind of puzzles Alex. So Alex contacts the plant accountant named Lou. And Lou tells Alex that there's three global performance measures, three measures that can tell us whether or not a company is making money. Net profit, return on investment, which is more of a relative type of measure, and cash flow. We need cash to stay alive. We can be making profit, but if we're not generating cash, we can't continue to finance our operations. And I think most of us would agree that these are good performance measures on a company basis. If a company's doing pretty well on these things, chances are it's doing pretty well. But what's the problem with these measures? Well, Alex starts to think about what do these performance measures really mean in his world, at the shop floor world. Down at the local level of the business, individual departments in the business, individual plants in the business if it's a manufacturing business, other individual locations if we're a retail chain, operating a distribution system, operating an airline. We've got to be able to link the decisions that we make down at that level, the lower or the functional areas of the business, up to the global level, the company level. And down at that local level, how do we know whether a decision that we make is a smart decision or not such a smart decision? And traditionally, companies use things like efficiency, cost per piece, utilization, some of the performance measures that have already been talked about in the goal and that we've kind of mentioned here. We need a way to do that. Unfortunately, net profit, return on investment, and cash flow, they don't work so well at the local level. As the chapter ends, Alex is thinking about Eddie. Remember, Eddie's been a supervisor in this business for years and years and years, and net profit, return on investment, cash flow, they don't mean anything to Eddie. You can't walk up to Eddie and say, Eddie, what was your net profit today, or what was your impact on net profit today? What was your return on investment today, Eddie? And that's very difficult to do for any local resource, any functional resource, any individual location in a business. We need measures to allow us to do that, but sometimes those measures don't have the effect that we have. The chapter winds up with Alex concluding that net profit, ROI, and cash flow, to Eddie, that stuff is just headquarters talk. So we need some better ways to link what Eddie does and to help Eddie make the right decisions for the company. So Jonah suggests three measures that the plant should use to evaluate its local level decisions, its plant level decisions, its departmental decisions, and he suggests throughput, inventory, and operating expense. Throughput is the money that the system generates through sales. Inventory is the money that the system invests in things it intends to sell. And operating expense is the money that the system spends turning inventory into throughput. In these chapters, there's a little bit of discussion about what these terms mean and do not mean, particularly with respect to inventory. There's some difference, as you can see in the book, in the way that Jonah suggests that inventory should be valued versus the way we typically value inventory using the value-added concept in our generally accepted accounting principles. Jonah does argue that we can use throughput, inventory, and operating expense to link local level decisions to global performance. We want to make decisions that increase throughput while holding inventory and operating expense steady, or maybe even decreasing them. And if we do that, we'll be better off. Or we want to do things that decrease inventory or decrease operating expense without having a negative impact on throughput. So I'd like to talk a little bit more about these, but before we do that, it would be useful to spend a little bit more time reviewing the conventional performance measures that companies use or have used for years and years and years. Many companies for years and years and years did not use throughput, inventory, and operating expense. They used measures like efficiency, utilization, and cost per piece. These have come up a little bit already in the goal. So let's break them down a little bit. Let's break those down a little bit and make sure we understand them. So we talked a little bit about efficiency already. Efficiency is the ratio of what you actually produce to what some standards that's expected of you over a particular time period. For example, if the standard is 100 pieces an hour and I work 7.5 hours and I produce 700 pieces, then my efficiency would be 700 over 750. I produced a little bit less than what was expected of me, so that's not so good. 100 is probably where I'm going to be expected to be. Anything more than 100 is good. Anything less than 100 is not so good. In a real situation, we'd convert all the output to standard hours. It gets a little bit more complex, and we don't really want to get into that in this class, but this basically gives you an idea of what efficiency is all about. So the important question to ask yourself is, how do you improve efficiency? Let's say you're Eddie, you're some other person on the shop floor, and the goal, well, you don't control the denominator, you don't control the standard, so really the only thing that you can do to improve efficiency is to produce more. If I produce more, it's going to increase the numerator, and that's going to make me look better. Let's talk about utilization. Utilization is basically a measure of the percentage of the time that I keep my resources busy. More formally, it's the ratio of direct time charged over clock time scheduled. Direct time charged is the time that we've actually spent running jobs in a manufacturing context. Clock time scheduled is the amount of time that resources are available. So the idea here is that if we're good managers, we'll keep our resources working all or most of the time that they're available. So here's kind of an example, give us a little bit better feel for this. Again, the thing I'd like us to think about is, if we're management or we're a departmental supervisor or something like that, how do we improve utilization? Well, we can't do a whole lot to improve the amount of time or change the amount of time that resources are available. The biggest impact that we're going to have on utilization is to keep all our resources working all the time, or keep all our resources working as much as possible. And again, that's going to make us look good on utilization. If we have high utilizations of all our resources, conventionally, top management is probably going to think we're pretty good managers. We're doing a pretty good job. Let's take a look at one more, and that's cost per piece. Remember, the robots drove down cost per piece, and everybody thought that that was really a great thing. Cost per piece is direct material cost plus direct labor cost plus overhead cost, and then we just divide that by the number of units processed. We typically do that on a work center by work center basis. So again, let's think about, if we're management in the goal, how are we going to improve our cost per piece? Well, which element do we really have control over? Let's say we're a production supervisor at Unico. We don't have a whole lot of control over overhead. We don't really have much control at all over direct material. Overhead is things like supervisory salaries, the light bill, those types of things. We can't really control, if we're, say, a production supervisor, what price we pay for direct material. Those are probably things that are negotiated company-wide by the company's procurement staff. So we really don't have a lot of control over that. We may think that we have a lot of control over direct labor, but often we don't even have a whole lot of control over direct labor. From time to time we lay people off, we hire people, but those are pretty long-term type decisions. Day to day, particularly if we're in a union type environment, if we're using full-time people or even salary people, we don't have a big impact on direct labor. So if we want to drive down our cost per piece, particularly in the short run, the kind of biggest bang for our buck, so to speak, is to focus on the denominator, and that's the amount of production. In other words, if production volumes are high, that's going to drive down cost per piece. It may impact direct material. Direct material may go up in direct proportion to the amount that we produce, but overhead certainly won't, and direct labor probably won't. At least a big portion of direct labor probably won't. So with all three of these performance measures, it seems that the biggest positive impact that we can have is by producing more stuff. Now that we understand a little bit more about conventional performance measurement, it makes sense to continue to think about the impact of the robots. Back when Jonah and Alex were talking at the airport, Jonah said, "If efficiency is increased on the robot, you must be running it all the time." And Alex responds, "We run the robot and all our resources all the time to maintain efficiency and keep our costs down." So they're running the robot all the time to maintain high utilization on the robot because they are producing more stuff with the robot. That's essentially what the robot allows them to do, is produce more stuff. It increases efficiency and it decreases cost per part as a function of increased volume, as we talked about in the previous slides. Yet paradoxically, late orders have gone up, inventories have gone up, and that's really frustrating to the folks in the plant. But it should make sense to us that this is happening because they're not selling anything more, but yet they're making more materials, at least some of the materials that go into making finished goods. So you're not getting more out, but you're putting more in, essentially. So the level of inventory in the system has got to go up. It's like cranking up the water on a bathtub, but not increasing the flow out of the bathtub. The water level is going to go up. So basically, when Jonah asks, "Are you selling more? Did you lay anybody off?" He's thinking about throughput, and he's thinking about operating expense. Unfortunately, there was no positive increase in throughput. There was no decrease in operating expense. And then Jonah also predicts that inventories have gone up and late orders have gone up, and that's because they're not selling anything else, but they're making more stuff. So as we move into Chapter 11, Alex actually gets to spend a little bit of time outside the plant. He goes on a hike with his son's Boy Scout troop, and he observes some things on the hike that have implications for managing his manufacturing facility, and indeed managing all types of resources in business contexts. So on the hike, remember, it took the troop a lot longer to get where it needed to go, and the troop also kind of spread out a lot more than Alex expected. And as Alex was thinking about those dynamics, he did a little experiment with some dice and some matchsticks to try to understand why that happened. Recall that in the dice game, the output was less than a naive person might expect. Let's try to understand what causes that a little bit more. If you were one person playing with one die, and let's say you rolled the die 20 times, and each time that you rolled the die, you took matchsticks out of a pile and moved them to another pile, what would be your output? In other words, how many matchsticks would you move? And then think about a two-person line where you're rolling a die and your friend is rolling a die. You're taking matchsticks, you're passing it to your friend, and then your friend, when he or she rolls, is taking matchsticks out of the pile that you're piling up in front of him or her, and they're moving them to the end of the line, so to speak. So you become a little production line with your friend. What would be the output there? Would we expect the same output if you and your friend played for the same amount of time, or more or less output? Well, if one person's playing, and let's say they're playing 20 rolls, the average roll is about 3.5 units. In other words, a die can either be a 1, 2, 3, 4, 5, or a 6, and the midpoint of that is 3.5. And if you roll a die about 20 times, you'll see that that's the case. If you write down your roll every time and you divide it by 20, it'll come out pretty close to 3.5. So one person, on average, would produce or process about 70 matchsticks in 20 rolls. And if you do that, you'll see that actually happens. You can actually do the experiment with two people fairly easily yourself as well. And if you do that, what you'll see is you get less than 70 matchsticks. And if you played it with three people, you'd get substantially less than 70 matchsticks. And the more people you play it with, in other words, the longer your line, the greater the departure from 70 is going to be. And that's because a lot of times when the downstream person, the second person, rolls a high roll, like a 4 or a 5 or a 6, he or she can't take advantage of that because there's not enough matches in the pile that the first person has created for them. In other words, there's not enough material in their queue, if they were a machine, for them to take advantage of their high rolls. But yet, whenever they have low rolls, they're penalized. The name for that is statistical fluctuations and dependent events. Statistical fluctuations basically means that each work center's potential output for any given period has an average, but there's also some variation around that average. If we're playing with dice, the average is 3.5, but the roll can vary from 1 to 6. It follows a uniform distribution. Dependent events means that multiple work centers have to complete their tasks in order for us to complete a unit. So a assembly line would be a classic example of dependent events. Everybody has to do their work, and they pretty much have to do it in a particular order. If we don't have dependent events, we won't have a problem. On the previous slide, we said that if you were playing the game by yourself, just as one work center, you were just rolling one die, you would be able to complete or to process about 70 matchsticks in 20 weeks, because you've still got the statistical fluctuations. You're rolling the die, but you don't have dependent events. You're not dependent on anybody else. You've got an unlimited supply of matchsticks. But if we put you together with another person and you have to play the game as a production line, like we saw in the goal, then that's where we get into a problem, because occasionally the first person in the line is going to starve the second person in the line. Remember, the most likely outcome is 3.5. So that's the most likely roll that the first person is going to roll at any given time. If the second person rolls a 5 or a 6, the most likely thing that happened before that was the first person rolled a 3 or a 4, and therefore the second person is not going to be able to take advantage of their high side variabilities. Yet their low side variabilities always hurt them. Anytime they roll a 1 or a 2, they can only move and process 1 or 2 chips. So the negatives always hurt you if you're the second person in line, the third person in line, the fourth person in line. But sometimes you can't take advantage of your high side variation, your good variation. We saw the same phenomenon in the hike. Now, there were 2 reasons why things didn't go as well as they could have gone on the hike. One of them, of course, was Herbie. He's maybe the more obvious one, and we'll talk a little bit more about Herbie in a couple of minutes. But the other one is because in a hike where people can't pass each other, you've got statistical fluctuations and dependent events. The average person hikes at about 2 miles per hour, but that's random. Right? Sometimes you're going to be going a little more than 2, sometimes you're going to be going a little less than 2, a lot of times you'll be going exactly 2. So there's some variation around that average of 2 miles per hour. If we can't pass each other, and I've got a little burst of energy, I can go a little bit faster than my average. Again, the most likely speed that you're going to be going if you're ahead of me, by definition, is the average. Remember, the average is the most, assuming a uniform distribution, the average is the most likely value that we're going to see. So generally, if I'm feeling capable of going more than 2 miles an hour, you, the person ahead of me, and the person ahead of you are going to be going 2 miles an hour. So I can't take advantage of that good variability, again, that high side variability. On the other hand, my low side variability when I'm hiking less than 2 miles an hour is going to slow down everybody behind me. If you're ahead of me, your low side variability is going to slow down me and again everybody behind me. So the negatives again hurt us, but as a group we usually can't take advantage of all the positives, and that's what's going to cause the line to spread out. Remember, this is called statistical fluctuations and dependent events. So looking at the last bullet point here on the slide here, if we take away the statistical fluctuations, this won't happen. If everybody hiked exactly 2 miles an hour all the time, the troop wouldn't spread out. By the same token, if we take away the dependent events, the problem won't happen. One person hiking alone is going to be able to hike 2 miles in an hour. They're going to be able to hike at their average, but the group hiking together can't hike at the average of a person working by themselves or hiking by themselves. You put people together and you don't let them pass, they become dependent on each other, and as long as we've got any kind of fluctuation in speeds, the troop's going to spread out. The entire troop is going to get where it's going slower than the average of any one person in the troop. This is a real important phenomenon to understand in business, because in business, typically what we have in most businesses are dependent events. In some businesses, one person does their thing and we're done, but in many businesses, whether it's manufacturing, whether it's construction, whether it's many different kinds of services, whether we're writing software code, we're doing a marketing campaign, you have multiple resources, and those resources depend on each other, and typically those resources have to do things in a particular order. And unfortunately, thinking about the statistical fluctuation side of it, there is variability in the time it takes any particular resource to do any particular task. We have a good business example of the phenomenon of statistical fluctuations and dependent events in the goal shortly after the hike, when they have to get a hot order out the door. They need to complete 100 units, and Pete's department and the robot both have to do work on the units. Pete's department passes the work onto the robot finishes the units. They've got 5 hours to get 100 units out the door, but really each department only has 4 hours because they don't begin with any work in process. So the first hour is going to consist of the robot being idle, and Pete's department then will pass its work to the robot at the end of the first hour, and the robot will start the second hour. So consequently, Pete's robot doesn't do anything in the 5th hour, and then the robot finishes in the 5th hour. So each one of these resources working in isolation, if it were working as just one person rolling a die, so to speak, has capacity of 25 units per hour. So we might expect that because each individual department has a capacity of 25 units per hour in 4 hours, they really shouldn't have any problem cranking out 100 units. But what happens when we put these two different departments together as a system consisting of two resources? So we put some dependency or some dependent events into the equation here. Well, let's make sure we understand what actually happened in the goal. The first hour, Pete's department produced 19 units. At the end of the first hour, Pete's department passed those 19 units on to the robot. And in the second hour, Pete's department processed 21 units, and the robot was able to produce those 19 units that Pete's department did in the first hour. The robot is generally not going to be as variable as a bunch of human beings doing a task. So at the end of the second hour, Pete's department passes those 21 units on to the robot. So in the third hour, Pete's department produces 28 units, and the robot produces 21 units. At the end of that time, those 28 units get passed to the robot. Pete's department does 32 units in that fourth hour. How many units does the robot do? Well, as it turns out, the robot does 25 units, either because there's no variability or very little variability in what the robot does from hour to hour, or because the robot was just average that hour. Okay, in the fifth hour, or at the end of the fourth hour, Pete's department passes those 32 units onto the robot. In the fifth hour, the robot again does 25 units. So let's kind of see what happened here. Pete's department produced 100 units, and of course 100 units is 25 over 4 hours is 25 units an hour, so Pete's department did exactly what it said it was going to do. On average, it produced 25 units. But what happened over here on the robot side of things is the robot did its 25 units in hour 4 and hour 5, but in hours 2 and hours 3, the robot was starved. Even if it had the capacity, the potential to do 25 units, which it did, it couldn't do them because Pete's department only fed it 19 units the first hour and 21 units the second hour. So the capacity of the robot, unfortunately, or the actual output of the robot, I should say, turned out to be quite a bit less than 100. So even though each one of these resources working together independently can do 25 units per hour, we put them together as dependency, and we've got some fluctuation in the actual output. Remember, the average here for Pete's department is 25 per hour, but sometimes it's more than 25, sometimes it's less than 25. It's just the average is 25. When we put those two different phenomena together, we can run into a problem, and we usually do run into a problem. The output of the whole is going to be less than the output of any individual in isolation.